Right, okay, so they've given me the structure of lactic acid there. Nice of them. It wants me to say what type of reaction occurs when it reacts with bases and metals. Well, with bases, of course, you've got an acid group here. So with bases, that's a neutralization reaction. Acid plus base gives us salt plus water, neutralization. With metals, an acid plus a metal, it's a redox reaction because a metal starts off as oxidation state 0, goes to whatever charge, it's ionic charge, in which case magnesium is 2+, redox reaction. Okay. And also produces hydrogen gas, of course. So, that's straightforward. The next thing it wants me to do is calculate the volume of hydrogen gas produced, measured at room temperature and pressure. Okay, so the first thing I need to do is realise that this guy is going to react with magnesium to give me that ion there, and I'm going to need 2 of those for the magnesium 2+ ion. So it's going to be that plus magnesium. So if I go, it's going to be lactic acid, and I need 2 of them, plus magnesium is going to give me Mg lactic acid twice, plus H2 gas. So for every 2 lactic acids, I make 1 hydrogen. So I first of all find the moles of lactic acid that I need. So let's do that up here. Moles of lactic acid is going to be the mass, 1.125 grams, divided by the molar mass, which is actually 90. That comes to 0.0125. Right. I need to times that, or divide that by 2 to find the moles of hydrogen. So moles of H2 is that number, 0.0125 divided by 2, which gives me 6.25 times 10 to the minus 3. And then for a volume of H2, you times that number by 24,000, because it's operating at room temperature and pressure, to give me 150 centimetres cubed. The final question in this little page is it wants me to give you the formula of the actual salt. If you count up, you've got 6 carbons, 10 hydrogens and 6 oxygens, so it's going to be C6H10O6 twice Mg, like so. Just to make sure you're happy, you've got 3, because that's a CH3 group there. You've got an H coming off there, and obviously you haven't got there, so 3, 4, 5 hydrogens there. And because you've got 2 of those, that gives you 10. The mark scheme seems to think it's 12 for some reason, which I don't think is right. Okay, so you can kind of let your imagination go wild here. Predicting 2 reactions of lactic acid, each involving a different functional group, but we can't include bases and metals because we've already done that one. So, let's go for the acid first. How about we do some esterification first of all? So the first one is we are going to react it. So the type of reaction is esterification. And we are going to, let's say, react it with methanol and concentrated sulfuric acid. And what will happen is the alcohol group will not be affected, but I will put a methyl group on the end there. For the secondary alcohol, well, let's oxidize it. So I can use K2Cr2O7, H+ conditions, and I would oxidize that to a ketone like so. Type of reaction is oxidation. Yeah, that's pretty nice for 4 marks, isn't it? Oh. Right, so amino acid times, and it is looking at glycine, the easiest amino acid, and it wants me to draw the skeletal formula of glycine. So I'm going to have an NH2 group, then on the other end I'm going to have a carboxylic acid group like so. Draw diagrams of stereoisomers B and C. So that's when copper 2 ions react. Okay, so we're on to amino acids now, and it wants me to draw the skeletal formula of the anion of glycine. So the anion glycine is I'm going to have lost that hydrogen on the carboxylic acid, so it will look like that. Obviously that's my CH2 group in the middle. Draw diagrams of stereoisomers B and C. That happens when this guy reacts with copper. So you will know that on both of those you've got a lone pair, so this is going to act as a bidentate ligand. So if we do it head on, it's going to be like so. They're square planar, so I'm going to have NH2, then I'm going to have da, 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 and that's O, like so, and then I could do the same up here. Like so. And actually that will be neutral overall, because obviously the ligand is 2, each one's got a minus charge, copper is 2 plus. Now for the other stereoisomer, what you can do, let's draw the left hand side one exactly the same, like so, but I'm going to draw the other one the other way, like so. And so those are your two stereoisomers. Right, the next question moves on to talk about aniline. And aniline actually has a CH3 group instead of the H group coming off here. And it asks why it will have more than 2 square planar stereoisomers. Well, it's because that carbon, this carbon now, if it's got a CH3 group, is now chiral. So it's because you've now got chiral centres in the complex as well, and therefore you're going to have more stereoisomers. Alright, so this is a slightly odd question. It says methanoic acid added to water. So methanoic acid has just got 1 carbon, like so. It's added to water. Acid-base equilibrium is set up containing 2 acid-base pairs. So just a mechanism for the forward reaction. So actually let's remove that hydrogen there and just pop on like so. I'm going to have water coming in like so with a lone pair. So he's going to come in and he would go like that, and that would give me the methanoate anion like so, plus H3O plus like so. Okay, this is quite an interesting question. It looks like, well, if you didn't have that first point, you would be completely stuffed. But the clue really is in this first bullet point here. It reacts by electrophilic substitution and electrophilic addition. If it reacts by electrophilic substitution, it must contain a benzene ring. If it reacts with electrophilic addition, it must contain a C-C double bond. Okay, it contains 7 peaks first of all, and it also is an organic acid, so it also contains COOH. Okay, it wants me to determine a possible structure for D. I can only have 7 peaks in the NMR, and the molecular ion peak comes in 148. So I know I've got this coming on, and I know I've got a carboxylic acid group. So at the moment I have got 1, 2, 3, 4, 5 carbon environments. I've got to be careful. I've got to now add in a carbon-carbon double bond. But let's say I put it there. Does that change my carbon environments? I need to have 7. 1, 2, 3, 4, 5, 6, 7. Okay, so I've got 7 carbon environments now. If you add all of this up, it comes to 148. So that's looking good. I've got a benzene ring for electrophilic substitution, a carbon-carbon double bond for electrophilic addition, and 7 peaks in my carbon NMR. Job done.